Okay. So what I'm going to do today is basically linear systems. Cameron, there's a couple of chairs over here if you want. We're going to talk about linear programming and a variant of that, or a version, it's called interlinear programming. And so I'll start with what is meant by linear system, and then kind of go on to a specific technique for linear systems called simplex, optimizing linear systems called simplex, and then we'll do an example that shows the power of linear programming, which is to solve network flow, a very classical problem in optimization using linear programming, and then I'll talk about interlinear programming and some of the constraints, and I think that's pretty much all I'll be able to cover in the time that we have. So I wanted to first start with a very brief review of what we did last time, and what we talked about last time was this whole issue of optimizing a system, and we talked about this notion of control variables and transfer functions and outputs. So we essentially have some O, which is the output objective function that we want to optimize, so the objective function, and that objective function is some function f, which is the transfer function, and of some set of control variables. Actually, I should keep the notation consistent and just put it over here. So I'm going to start using vectors. So I'm going to try and remember to use blue for vectors. Let me see how well it shows up. Is that visible in the back? Yeah? Okay. Is that visible in the video? All right. So let's just say blue means vector because bold doesn't really show up here, and that's your control. And then you have some fixed parameters, and we'll just call that f, capital F, for fixed parameters, and that's some vector of fixed parameters as well. Okay, so we have an objective function, we have some transfer function, it's objective function, which is the objective that we want to optimize, which has some transfer function and the control and fixed. So what we do is we take the system, we model it, figure out all the fixed quantities, that's f. We find out all the knobs we can turn, that's x. We figure out how these affect the output, that's your transfer function. Then we kind of tune the knobs, turn the knobs, so that this gets maximized or minimized. That's sort of optimization in a nutshell. Now, the first system we looked at was this trivial system, which looked like this. On this axis, I had x, and on this y-axis, actually, I had O. And we looked at it, it looked like this, and we found that there's a single point at which you optimize that, and that was this value over here. And we saw that sort of geometrically. And this one is straightforward. You have single dimension, single variable x, and you can just move that around. X was the sending rate, and as you move the sending rate, you very clearly saw that there's a single peaked point, and you're done. Now, things got a bit more difficult when we had two variables, x1 and x2. When you have x1 and x2, the two variables that you're trying to optimize, and we had the constraint x1 plus x2 equals 1. Now, we knew that the objective function lay on this line over here because of the constraint over there. However, we were not able to draw O as well because, the three-dimensional thing. And if you were to draw it, you'd sort of see a function which was minimum over here. It was -1. I guess it went to something over here, 2 or 3, whatever it was over here. All right. So let's say it's 2. Anyway, it goes up, and we found that O increased in this direction. So again, you can sort of visualize that. Then we had 3 dimensions. It goes like this. We have sort of these 3 axes, x1, x2, x3, and the constraints were in the form of a plane which said that all the valid values of the x lie on this constraint plane, and we were able to draw these isoquants, and we found that as we pull the plane, as we kind of moved along in this direction, in the positive x direction, looked at the intersections, the maximum value is achieved at this point over here. So we have 3 dimensions over here, and now we run out of space. We can't actually draw anything anymore. So the question we want to ask today, and kind of should take most of the lecture today, is to think about linear systems where we have not 1, 2, or 3 of the things, but perhaps you have 100,000 variables. Okay, so in that case, you have you can't really draw 100,000 axes. So how do you actually solve these things? What's actually going on? what we wanted to do initially was to develop the intuition, which is what is being done over here, and then we jump from intuition to formalism, okay, and then from formalism to an example. So 3 steps. So I want to basically go through pretty much the whole course in this way. First intuition, then formalism, and then an example. There is a chair. There are some chairs over here if you want to sit down. It's probably easier to take notes sitting down than standing up. Okay, so what I'm going to talk about is what happens when you have 100,000 variables. So remember that the constraints that we had were on the x. Okay, so we basically said in this case we had the constraint function, which was that x1 is greater than or equal to 0, x2 is greater than or equal to 0, x3 is greater than or equal to 0, and x1 plus x2 plus x3 equals 1. All right? Now, what I can do is, let's just ignore the geometry for just a moment, and we'll go into simply looking at the equations, and let's just say we have 10 variables for the sake of argument. Now, what I can do is write down these things like this. x1 is greater than or equal to 0, all the way up to x10 is greater than or equal to 0. So we're just saying everything is in the positive values of x. That's easy enough to do. Now, here I had a certain number of constraints on these, adding them up to 1. I can actually write it down something like this. Let's say we have some constants, and the constants are a1 up to a10, okay? And actually, let me just keep it a bit more. Okay, let's just start with this, a1 to a10, and I can do something like this. I can say a1 x1 plus a2 x2 plus a10 x10 equals c1, where c is some constant. This is just a generalization of this over here. And now this defines a plane in the 3-dimensional space. x1 plus x3 equals 1 defines a plane. This one is, by generalization, defining a hyperplane in some 10-dimensional space. Okay, so we don't really need to worry about what it looks like. In fact, we can't. So we just say, look, this is a constraint function. It's a hyperplane. Okay, just to give you a sense of how horrible it is, I'm just going to pause for a minute, and so I'm going to ask you this question. What does a hyperplane look like in 4 dimensions? Okay, so we know what a plane looks like in 3 dimensions. So I have 3 dimensions, that's a plane. We know what a plane is. This is actually not an infinite plane, it's just a finite plane. But an infinite plane is nothing more than a sheet of paper that extends, the width of the universe. It's not a big deal. What does a hyperplane in 4 dimensions look like? Okay. Does anybody want to guess what it looks like? What does a hyperplane look like in 4 dimensions? A hyperplane in 4 dimensions. Somebody? Yes?
It would depend on what you define the 4th dimension to be.
Let's say time.
Okay, so it'd be a plane that changes over time.
Plane that changes over time. How? So, okay, let me just give you a simple example of this. A plane that changes over time is sort of correct, but to understand this, here is the thing, and this actually, when I first realized it, was very interesting to, it was like, wow, that's great. So if you take a snapshot of the whole universe at time, any time, right now, the whole universe, you, me, everything, the whole earth, the universe, everything, that's a plane in 4 dimensions. The entire universe is a plane in 4 dimensions. And the reason you can think about it, how to understand it is like this. What does a plane do? A plane separates the space into 2 regions. One is on this side, one is on that side. The whole universe at this point in time separates all prior events from all future events. So any 4-dimensional thing that extends from future to past must cross through this entire universe, right? In other words, you just say t equals some value x, or t equals some value 0, and we leave all the other variables, x1, x2, x3, unbound. That means you get every point in the universe. So a plane in 4 dimensions is the whole universe at that moment in time. It's very simple once you think about it. Okay, that's just an orthogonal plane. This is a plane that's tilted. What happens when you think about a tilting plane in 4 dimensions? And I'll let you think about it. It's a bit interesting. But what it is essentially a solid, okay, as big as you want, which is kind of moving through space and time at the same time. So it's not exactly a plane that changes over time, but it's kind of a solid, depending on how big you make it, that moves through time and space. And again, it's a great thing to think about if you're trying to fall asleep. Okay, So I'll leave that as a homework exercise. What does a non-orthogonal plane look like in 4 dimensions? And in 10 dimensions, forget about it. Okay. So we go back into the formalism over here. And what we're going to do here is to say I have some constraints on this. This defines a 10-dimensional plane. It's a 9-dimensional object in 10-dimensional space because it's 1 dimension less. Okay, now the thing is over here I had a single constraint, but why not have more? You know, there's nothing that prevents us from having more. So we can generalize this in the following way. We can say, let's start using matrix notation. So we can say, well, we have A11. Instead of A1, I'm going to have A11 x1 plus A12 x2 plus A110 x10 equals C1. Actually, I think I should be using B1 because that's what, yeah, let's just use B1 because that's the standard notation. A21 x1 plus A2 10 x10 equals B2, etc. Okay? And let's say over here I have A10 1 x1 plus A10 10 x10 equals B10. Okay? So in this case, what I've defined is a set of 10 constraints, okay, with the 100 constants and 10 variables, and and we have basically 10 simultaneous equations. So if I do this, I have a problem right away. Okay, so what's the problem? Okay, what is the problem if I have these many constraints on the system? Yes, what's your name? Gary. Gary, yeah.
You can have no solution. You have one factor.
That's right. So when you have a system of simultaneous linear equations in this form, basically there's nothing to optimize. You're kind of out of luck. Either you have one solution, in which case you have unique values for all the variables, which solves the equation, or you have basically redundant system, okay, in which case you could have removed, eliminated some equations, so you have fewer than that, which is a many solutions case. Or you have inconsistency, in which case there's no solution possible, right? Which basically comes down to something like x1 equals 1 and x1 equals 2 at the same time. Of course, that's impossible, so we have no solution at all. So in the case we have no solution, we're out of luck. We have an impossible system. The constraints are insoluble. We cannot optimize because the constraints are what are called over-constrained. You've defined it in too many constraints. There's no way you can do anything about it. So you can't optimize. You're out of luck. If we have a system which has one solution, again, there's nothing to do. You have exactly one point in space, in 10-dimensional space, that satisfies the system. So there's no knobs to tune. The knobs have all been locked down, and that's all that you can do. It's a determined system. It's a deterministic system. What happens if we have more solutions than one? Okay, it means we have some systems that are some equations that are redundant. Basically, what that means is that I actually don't have 10 equations. I only have like 7 or 8. Now we have something to do. Okay, if you have 7 or 8 or even 9 equations, and not all 10, then what we can do is that the one free variable, okay, allows us to tune the knob. That's the free knob, and all the other things are what they are. Okay, you can change one knob, and then the objective function will change as you change the knob. Okay, so essentially, if you have one free knob, it's just like this. If you have 2 free knobs, it looks like that. If you have 3 free knobs, it looks like that, and so on. And of course, in the limit case, we have 10 free knobs. It can be anywhere. Okay. For those of you who studied linear systems or linear algebra at all, what you're basically saying is that the rank of this matrix cannot be 10. Okay. If it's if you have 10 variables, x1 to x10, the rank of this must be smaller than that. It should be 9 or smaller. Otherwise, if the rank is 10, I'm out of luck. It's a fully. So these are the opposite of what you said in linear systems. You're doing Gauss elimination or any kind of solution of linear systems. You want to make the system rank same as the number of variables. We have a unique solution. In optimization, we don't have that. What we want to do is we want to ensure that the rank of this system over here is less than the number of variables. Otherwise, there's nothing for us to do. Okay? So that is exactly the right answer over there. So is that clear what's going on over here? So in the formal system, what happens is you write down the constraints, and the first thing we do is look at the rank. If the rank of this matrix is too large, either it's overdetermined or there's no solution. It's only one solution, and you just run Gauss elimination. You're done, and that's the easy case. So we're going to assume that this has a rank less than the number of variables. Okay. All right. So, any questions on this so far? Okay. Yes.
So, just a general question: why do they have to be only 10 constraints? Can't there be more constraints?
Oh, the question is, why can't we have more than 10 constraints? If you have more than 10, it becomes over-constrained. Okay. If you have more than 10 independent constraints, what you can very quickly do is to show that we have inconsistent constraints. It's not, we cannot solve the equation. We'll end up with essentially like this one, x1 should be 2 values at the same time. How can we do that? Let's say we have 20 equations. We take any 10 of them, they're independent, solve for them, right? We have a solution because we can just eliminate them one or the other using Gaussian elimination. We get 10 values. Plug into the 11th equation. Either it fits in or it doesn't. If it matches the 11th equation, then that was a redundant equation. If it doesn't match it, it's going to be overdetermined, right? It's inconsistent. So either way, you're out of luck, right? So that's why we don't care about more than 10. Yes, Chan.
So even if the rank is less than 10, the system can also be inconsistent?
Yes, even if it's less than 10, it can still be inconsistent. But it's a quick check. If you have more than 10, already you know right away there could be a problem. Yeah, that's right. Yeah, so you can have inconsistency even with 2 equations, right? I can give you right here this equation, x1 equals 1, x1 equals 2. Okay? Right? This has much lower rank than 10, but it's already inconsistent, so that's easy. Not a big deal. Okay. Any questions? Okay, so what we've done now is basically we are now getting into the sort of the heart of how do we do linear optimization, which is we reduce the physical problem, the problem that you want to solve into a linear system. And now I can write down the linear system. It's easy. I'll just take this matrix notation over here and okay, I can erase this over here. And let me keep this over here. And the solution is this. So AX equals B. That's my constraint system right there. It's easy. When you have blue chalk, everything is easy. Okay? So what we're saying is that we have some set of control variables. Actually, I should use small x just to be consistent over here. X is the set of control values. X is now a vector. A is the constraint matrix. Multiplied by this is B. And that's just that whole pile of equations over there. I just wrote it in matrix notation, and that's what we have over here. And so that's the formal definition of a linear system. Now, why is it linear? Well, it's because if you look at this, any of these equations, let's say A1, 5, x1 plus, A 5, 1, x1 plus A 5, 2, x2, etc. One of these, A 5, 10, x10 equals B5. Let's say that's the fifth equation over here. As you can see, it's just a sum of products, right, of constants. It's a linear system, okay? Linear system basically means if I change any of these x1 by some epsilon, the whole thing goes up by A phi 2 epsilon. So it's a linear transform of the whole equation, So I don't want to go too much into this, but essentially anything that looks in this form is by definition a linear system. And so we have system of linear equations, and that's what we have over here. Okay. So in the general case, what we're going to do is that we're going to take the system, we're going to find out the control variables, look at the constants, and try to come up with the set of constraints over here. And then what linear programming is nothing more than saying, how do we find the maximum value of O given this? Okay. So that's what I'm going to talk about in simplex. But I guess I should be, this is just about time for a break. So let me stop here, and then after the break, we'll kind of go into what simplex does. Okay. I want to go into this. Okay. So I'm going to continue now, and I'm going to go into the formal definition of what a linear system looks like. So a linear system is going to be a set of constraints where Ax equals B. All right. And typically, we also have the relationship that x is greater than the one vector 1. Okay, so or greater than equal to, sorry, what am I saying? The 0 vector, x greater than equal to 0 and ax equal to b. So we have positive x. Now it turns out in some cases that we may have inequality constraints. So we may have something like this, a11, this one over here, instead of having a 0 equal to b5, we may have this thing like this, greater than equal to b5. Okay, so this basically says that the value lies, in some sense greater than some hyperplane over here. In order to get rid of this, we use a simple trick. What we do is we rewrite this with extra variable called a surplus variable, and we just say a51 x1 plus a52 x2 plus and so on plus a510 x10, okay, plus, okay, or in this case actually minus s5 equals b5, right? If these things is greater than b5, then if you subtract s5 from it, it should be equal to b5, where s is yet another variable. What I've done is I just made it 11 dimensional instead of 10. Okay, but between friends, what's the difference? 10 and 11 dimensions, no big deal. We do that over here. This is over here called actually a lag variable. And if we have a less than equal to b5, we could have done plus s5, and that's called a surplus variable. And by introducing surplus and lag variables, we can transform inequalities into equalities. Okay, and that means we can still retain this, what's called the standard form, ax equals b, x greater than equal to 0. So this is the standard form. Okay, so this means the standard form sort of is universal, and so in typical systems we end up just specifying, equalities. We don't really need to care about inequalities. Okay, now it turns out that in practice you don't need to know too much about how it's solved. So I'm going to do two things. First, I'm going to do an example showing you how to set up the linear system, because that actually turns out to be the hard part. And once you've done the setting up, you give it to what's called a solver, a linear programming solver. And these solvers do some things. I'll talk about what they do actually in solution. And that's a simplex algorithm. So most of the focus here is how do you set up the linear system? Because when you read a paper, what will happen is it will say, okay, we solve this using linear programming, and they say, our objective function is this, and these are our constraints. And they write down the constraints and say, we use so-and-so solver, and it solved it for us. Okay, we don't really need to worry more about it. So here I'm going to tell you how to write this set of constraints down, and then after that, I'll give you some intuition how a solver works. So let's take the following example, and that will tell you what these constraints and so on mean. Is this part visible to everybody clearly in the back? Over here, if I write over here, it's clear? Yeah. Okay, so I'm going to take an example, and what we have is we have some company over here, and this company has got two network connections, and this is what's called multihoming. This is quite common. For example, University of Waterloo has got a connection to something called Orion network, and it also has a connection to something else. I can't remember what it's called. So we have two connections. Why? Because if this ISP goes down, this other ISP is available, so chances are pretty good that you won't be completely gone. So we'll call this provider this provider as, okay, I'm just going to tell you what the difference is. So let's say that these two providers for the company come with different what are called service level agreements, or SLAs, right? So SLA is like this. It says, I'm going to charge you this cost per byte, C, you can think of C dollars per byte. And I'm also going to give you a delay guarantee of some delay bound. Okay? So that's a service level agreement. So the ISP comes to the IT person in the company and says, you know what, I'll guarantee that your access to the internet backbone, the delay shall not exceed some delay bound, and for that I'm going to charge you so many dollars per byte. It's not unlimited, but I'm going to charge you, let's say, $1 a gigabyte, which is typically what people charge today. So this is the service level agreement. Now this company has got in it, let's say, two different applications, A and B. Okay, And now what the company wants to do is that it wants to decide where to send the data from A and where to send the data from B onto the internet. Okay, so this is actually something that happens quite often. Typically, example of this A and B would be, for example, B might be sort of web traffic, and you know what this web traffic is because it's going on port 80, and this one over here could be voice over IP traffic, and we know it's voice over IP traffic. It's going to a different port, whatever that port is. So this actually shows up very, very commonly. All right. Now what we want to do is this. We define that application A, okay, has, and now so we have the, okay, so let me step back a minute. So we have these two ISPs over here, and let's call them high and low, okay. High ISP, so I have ISP high, gives you a low delay and a high cost, high dollar per byte. And the ISP low, on the other hand, gives you high delay and a low dollar per byte. And this is again a pretty typical trade-off. You know, the lower the delay you want, the more you have to pay per byte. So the optimization problem is, again stated in words, is given some amount of traffic, I want to make sure all the traffic gets served. Okay, obviously I don't want to drop anything. How do I partition the traffic between high and low so that, you know, I spend the least amount of money? Okay, so let's start putting some numbers in there and some terminology in there, which will make our life easier. Okay. So the first question you have to ask yourself is, okay, what are the control parameters? What do we actually have control over? And what are the fixed parameters? Okay, so in this case, we know that the control parameter is how much traffic you send on ISP A, on ISP high and ISP low, right? And in fact, what we want to do is we want to know how much traffic from application A you want to send on ISP high, how much traffic on ISP B, so application B. So we define the variable X, A, H to be the amount of traffic from application A on high, similarly X, A, L as on low, X, B, H, and X, B, L as these as the corresponding parameters. So this is the amount of traffic sent by A on high, by A on low, by B on high, B on low. Okay. Now let's say the total traffic from A let's call that TA, and similarly we can define total traffic from B as TB. We immediately get the following. Since we don't want traffic to be dropped, we get that XAH plus XAL equals TA, and XBH plus XBL equals TB. These two correspond to don't drop traffic. Okay, so when you hear the word don't drop traffic, then you say, okay, these equations come out from there. So that's the modeling step. Okay. Now the next thing we want to do is to say, let's minimize the cost. So how much cost are we going to pay? Well, let's go back over here. We had the C dollar per byte. Let's call the cost CH and CL, right? Obviously, those are the costs for per byte for the high and low. And so the cost is nothing more than XAL plus XBL times CL plus XAH plus XBH times CH, right? That's how much stuff is sent on L, that's how much stuff is sent on H. You multiply those two, I get the total cost, okay? So we have already got some measure of how to measure the cost. Now, but what we want to optimize is not just the cost. Why is that? Well, you can optimize the, you know, we are not taking into account over here the benefit that we're getting over here, the benefit from low delay or high delay. We want to actually measure the benefit as well. Okay, otherwise, we're not actually representing the problem properly. So what we want to do is to somehow measure the benefit. Now, what we're going to do to measure benefit is that we're going to have the following, assume that we have the following 4 variables, and this is B, A, L, B, A, H. So what are these two? This is the benefit that application A gets from sending on L and from getting on H. So let's say A is delay sensitive. Its benefit from sending on the low cost link is not as much as we're sending on the high cost link, because here the delay is lower. And similarly, we can have benefit B, B, L, and B, B, H. Okay, so these are the benefits that you decide. Okay, I get lots of benefit from sending VoIP on low delay link, but I don't get much benefit from sending VoIP on this bulk link or on this other link. So if you have this, then we can actually define the following. We want to optimize, or typically we want to optimize this: cost minus benefit. Sorry, benefit minus cost. Okay? That's what you want to do typically. You want to say, this is how much benefit, it comes at this cost, so I want to maximize the benefit minus cost. And now we can write down the benefit minus cost like this. It's the benefit from A on sending on L times XL, right? That's the benefit, plus benefit from A on sending on XAL, XAH, plus benefit from B to sending on H, XBH, plus BBL, XBL. Those are the benefits minus the cost. So let's say this cost over here, that's just, we plug that in over here, minus cost. And this, we say, is objective function O. Okay? So what's going on is the O is just these 4 terms minus these 4 terms. That's the objective function. And the constraints are these two plus the constraint that XAH, XAL, XBH, XBL are all greater than or equal to 0, positive. Okay, we can't send negative traffic. Okay, so that is how we model the system, right? We've got a linear objective function expressed in terms of the 4 variables, A, L, AH, BL, BH. Those are the 4 knobs you can turn. Okay, we have some constant parameters, which are these guys over here, as well as these guys over here. So we have 6 fixed parameters, the costs and the benefits. And we have the objective function. And we have 2 constraints also in terms of 2 other fixed parameters. And we can plug it into a linear solver. At the end of it will tell you the values of XAH, XAL, BH, and BL. And that's how much you should be sending on each of them. And that's the solution. Okay, that optimizes the system. Okay. Any questions about this so far? Yes, Omar.
Are these benefits per byte?
The benefits over here are defined in terms of per byte benefit. So basically it says this is the amount of benefit I get from sending 1 byte of traffic from B on H. So if I send more, I get more benefit. Because cost is per byte, benefit also has to be per byte. Right. Any other questions? So one can actually imagine doing this in practice, right? I mean, we may at the end of this course, you may go to some company and they say, okay, we want to optimize our multi-homing. You can say, okay, what are your costs per byte from your SLA? What kind of benefit? You know, you can ask them what benefits they have, and also how much traffic are you getting? You get these 2, and then you can plug this all in, and you can essentially find, using symbols, which I'll get to in a minute, the solution. Okay. So the point I'm trying to get across is that, you know, when you talk about linear systems and so on and so forth, it's not just, you know, for the sake of studying math. Okay, there is something going on over here which you can actually use, and this is an example of modeling. Once you get the modeling right, you can, you know, make use of it in a fairly practical situation over here. Okay. Any other? I should point out that I'm doing something sort of under the cover over here, sort of like what Omar points out, which is that I'm assuming this is linear. Okay, it means if I send lots and lots of data, I get lots and lots of benefit. Typically, human beings don't have linear benefits. Benefits typically look like what's called a sigmoidal curve. Okay, you get quite a bit of benefit. You get no benefit if you have very little. You get a lot of gain, and after that you saturate. Okay, so this is like my kids. I give them a small amount of candy, they don't like it. It's too much. You give them 1/100th of a molecule of candy. It's like, what's the point? It's nothing. Once you get reasonable amount, they're very happy. At this point, they fall sick. Okay, so they can either go down, okay, or they just get no more benefit after that. They saturated the capacity to eat candy. Okay, so this is obviously nonlinear. However, linear system assumes everything is linear, so we can use it in this range. Okay, it can be approximated as a linear value, and we can have 2-part or 3-part linear and do separate optimization on each of those things. However, those topics are not. I'm not going to consider them over here. Just going to tell you that this looks nice, but there are some definite problems with it. Okay. Any other questions about this? All right, so at this point, you should already be in a position to start reading papers on that use linear optimization and figure out how it works. Okay, so the next 10 minutes or so before the next break, I'm going to give you an idea of how to solve this system like here. And so for solving the system, I'm going to go back to this intuition we had earlier. I'm going to just draw the 3-dimensional case just to remind you. We had this plane over here. Actually, in this case, what we had was not just a plane. We had several planes. Okay, we had this plane that said you have to be in the positive quadrant. So you had this plane, and then you had this plane, and you had that plane. So if you look at those planes and the constraint plane, you actually have 4 constraint planes, and that defines sort of a tetrahedron. Okay, so tetrahedron over here, which is actually this tetrahedron over here. Okay, so is that clear? I mean, because that's the positive x1, positive x2, positive x3, and so we get this nice looking solid. And what I said last time is that in a linear system, we have this nice property that the optimal point lies at one of the vertices, okay, or one of the faces of one of the lines, but just for now, ignoring those cases, it lies at one of the vertices. Okay, what is a vertex? A vertex is just an assignment of values to x1, x2, x3. Okay, that's what a vertex is. So if you generalize this to more dimensions, what happens is that the object we get over here is called a polytope. And in particular, we are interested in polytopes that satisfy the property that's convex polytope. And what a convex polytope means is that if I take some point here and I take some point here on the edges and draw a line, basically I'm inside the polytope at the whole time. I don't actually go out and come back in again. Okay, so we're looking at convex polytopes. Okay, and convexity can be more formally defined, but it's intuitively the fact that I can draw any arc, or sorry, any chord lies below the arc. For example, in this function that's convex, but in this case, if I have a function that looks like this, so this is not convex because I can I'm going out and then back in again. So convexity is this nice kind of compactness property. Everything is nice and clean. Convex polytopes arise from these hyperplanes, okay, from the intersection of hyperplanes. So in this case, I have 4 planes, and the 4 planes together give me this convex tetrahedron over here. Okay, you can't create anything other than a convex polytope from these 4 planes. In multiple dimensions or higher dimensions, we have similar kind of effect where we define these hyperplanes. Now the hyperplanes are going to be inequalities, generally speaking. If you want to think about it, equalities also work out, but it's harder to imagine it. But in the hyperplane, so we have a set of hyperplanes. Each inequality gives us a hyperplane, and then you say, okay, I'm greater than or I'm less than, so I'm in some direction. Okay, so each hyperplane gives me some direction of being away from, and then I look at the space which is bounded by all these hyperplanes. That gives me a convex polytope. Okay. Now what we're going to do is we're going to choose one vertex on the convex polytope to begin with, and then we're going to go from vertex to vertex to vertex, hopping along the vertices. Why are we going to do that? Because we can prove, and I won't show it here, we can prove that the optimal point, the optimal value happens at a vertex. Okay, optimal value of the system is found at one of the vertices of the system. At a vertex, what happens is that essentially the xi's have some extremal value. Okay, if for example, if you're saying x1 is greater than or equal to 0, then at a vertex one of the x1 is equal to 0. Okay, because we don't have like 0.5 and all this other stuff. It's going to be exactly on the constraint. By the way, the values don't need to be integers. You can say x1, we can say x1 plus, x1 is greater than or equal to, or we can come up with some value where the extremal points are not 0. It doesn't just have to be 0. It can be any real number actually. But the point is that the optimal point happens at the vertices. So we don't need to go inside the polytope. We can just stay on the vertices, kind of working our way around. So how do we find it? The way we find it is like this. If you look at the matrix, representation, we have AX equals B as the solution. Okay, and I'm going to sort of state without proof that this corresponds to a polytope. All right. Now what I'm going to do is I can find a submatrix of A which is full rank, which can be solved. How do I do that? Because the matrix A consists of a whole bunch of equations like so, and what it is that I have fewer equations, okay, than I need. Okay, what I can do is I can take fewer variables. Let's say I have, in this case, 4 equations. I'll take 4 variables and set the remaining variables to 0, okay, and solve it. Now clearly this satisfies the system. Why does it satisfy the system? Because all of these can be anything. They're free variables. I can just set them all to 0, and that also will solve the system because infinitely many solutions. So I can find a solution. Okay, a solution to this system, by definition, is a vertex of this polytope. Okay, right? It's a vertex of the polytope. Once I find a vertex, what I need to do is to find another vertex. In other words, another value of xi such that they satisfy the system over here. And that's really what the simplex system is doing. So if you can imagine the polytope as being something like this, okay, and I can't really draw it, but it has some vertex over here which I find by having this reduced number of values and setting all the others to 0, that gives me the first vertex. Then what I have to do is to find a way of finding all the neighboring vertices of this vertex, okay, all the neighboring vertices. The neighboring vertices are essentially solutions where all the xi's remain the same except for one xi that changed. Okay, so we change just one of the values of the xi's, and that gives us a new vertex. So if we have a lot of different values over here, we say, okay, I'm going to pick this one, and I'm going to change that, and then all the others will change slightly, but this only one actually changed. The other ones may or may not change, and that gives me another vertex over here, and you kind of go to the next vertex, and so on and so forth. I'm being somewhat vague over here because the details are quite complex, but the intuition is that we choose a vertex, we generate all the neighboring vertices, we find the value of the objective function at each of these vertices, and we pick the vertex which has the greatest improvement in the objective function. We go there, we can repeat this, and we can essentially climb our hill all the way up until we reach a point such that all the neighbors around it have a lower value of the objective function. At this point, you're done because this is the optimal point. Okay? And what the simplex system does is to find a trajectory, series of vertices, one to the other, such that you find the optimal point reasonably fast. Now, it turns out that in theory, simplex can be very bad. Okay? It's possible to construct these bizarre pathological polytopes such that simplex will go around, round and round and round and take exponential time before it reaches the optimal point. It will find the optimal point, but it's like going on a hill in a spiral, going round and round the hill in a spiral, and you will get to the top, but it's not the same as the direct path. While pathological cases can be constructed, it turns out that in practice, simplex pretty much finds it, very, very fast. Okay, so that's not a problem. There are 2 other methods that have been proposed to solve this problem. One is called the ellipse method. The ellipse method guarantees cubic time, or order of n cubed. So if you have 100,000 variables, it's order of 100,000 cubed, okay, which is big enough. But anyway, it guarantees a polynomial time solution. However, it's far more complex to implement, and so in practice, people don't use ellipse method. One of the biggest breakthroughs in optimization happened about 20 years ago when when it was found that to get to the optimal point, instead of following the vertices, you can actually go into the inside of the polytope and then out again. Okay, so we don't have to stay on the vertices. We can find an interior point and then go out. Okay, and this cuts down the amount of time to find the maximum a lot. It makes a huge improvement, and these are what I call the interior point methods. So in other words, if you over here, for example, instead of following the vertex from here to here and here, I might choose the intermediate point inside and then jump to the corner over here. And so these interior point methods are actually what people use a lot today. And again, the details are well beyond the scope. But the person who invented it is a guy called Karmakar. Is what he's famous for. He's more famous for because the method was also the first algorithm to be patented, for which a patent was granted. Until then, the U.S. Patent Office said you can't patent algorithms. But Karmakar at the time worked for Bell Labs, and they managed to convince the patent office it should be patented. So today, all airline scheduling in the world pretty much is done through interior point methods. So you say, here are all the planes. You can set up the equations. Every plane cannot travel more than so many thousand kilometers a day. This is how much gas they have. These are the cities you want to transfer to. These are all the people who want to come and go, et cetera, et cetera. And you crank away at this. It typically has a few million variables. You crank away. At the end of it, it says, this is the way the plane should go, and that's the way they fly them. Because you have to fly a plane, so it goes from here to some other point, picks up people, picks up petrol, gets maintenance, and then goes somewhere else and comes back. And so you have to schedule all the people, all the planes, all the fuel, and it's a lot of variables. So you throw this whole big thing into the system, you run the interior point method, and it tells you this is what you should do, and it cannot be done by hand. It has to be done using linear programming. So that's one of the grand successes of linear programming is airline scheduling. So next time your flight gets delayed, you know whom to blame. It's this guy over here. Okay. Any questions about this?
I was wondering why you only consider the convex polytope, because we can break any form of polytope into convex form, the chunks of convex.
Right.
And we can solve individually for all the convex, and we can see the optimal value.
Yeah. Okay. So what's your name for a second? Jalaj. Okay. Yeah. So for classical simplex, it's necessary that the entire system be one single convex polytope. What you're saying is that we can take a system which is not convex and partition it into sub-portions, which can then be individually optimized. Yes, that can be done, but again, I'm not trying to solve that. Right? I'm just going to tell you this is the Eiffel Tower. Okay, this is just the big picture. You have to understand that classical techniques work on convex polytopes. However, there are many, many advanced techniques that I'm not going into. So this is just to give you a taste of what it looks like. So the goal here at some level is you see the paper and somebody says, okay, I have a linear program, and they write down these equations. Instead of saying, oh, I don't know what it means, now you have some idea what it means. Hopefully you can understand what's going on. These are the constraints. This is the objective function. You run it, you sort of plug it in, and you see, okay. And then the first thing you should do in reading a paper like this is, okay, is it really linear? Is there some kind of saturation effect going on? Okay, why is it being modeled in a linear fashion? And once you do that, then the rest of it is really not that important, okay, because how it gets solved. Okay. Any other questions? Yes.
In order to find the vertices which gives us the optimal values, can't we define convex hyperplanes and then use gradient methods to go to the direction of that vertex?
Yes. That's what we do. When I say find the neighbor which has the highest increase in the objective function, that is a gradient method. We're going along the vertices in the gradient, right?
So, but assume that none of the neighbor vertices have a value better than the current vertex.
If none of the neighbors have a value higher, because of convexity, you can prove that then this is the optimal point. The only point, the only vertex whose neighbors have a lower value is the optimal point. Okay. That's why its convexity is important. And when we talk about nonlinear optimization, you'll see that this property goes away when you have nonlinear systems. But in linear systems, we have this nice property that just checking all the neighbors is all you really need to do to guarantee that you're at an optimal point. Any other questions? Okay. Let's see. I guess I'm supposed to. Okay, let's take a break here. And then, all right. Because all of us are getting ready for lunch. All right. So, linear programming, as I've shown over here, then, just to sum up, is basically saying I'm going to define a set of variables, okay, the xi's. I'm going to find a set of constraints and constants. Constraints are the equations, constants are what's going on the right-hand side. And then when I put this together, I'm going to find a way, simplex or some other technique, which allows me to find the optimal value of the objective function subject to constraints. Okay, so that's sort of something we have in our pocket right now. How can we use it? Okay, so I want to illustrate the power of linear programming by using it to solve something that you solve in a different way, hopefully in your undergrad class, which is network flow. And so, how many of you studied max cut min flow for network flow graphs? Okay, so a few of you kind of are familiar with the max cut min flow, which actually is the optimal algorithm, but we'll do it a different way. It's not. This is not the optimal algorithm, but it's just interesting to see how it can be done. So, what's a network flow problem? So the origin of this is the following. We have some kind of road network between these warehouses. So we have some set of warehouses and some set of roads. It looks like a graph, as you can imagine. And each warehouse, for the moment, we assume has infinite capacity. We can put whatever we want in there. Okay. However, the roadways have a finite capacity. So we can only send a certain amount of goods from this warehouse to this warehouse during the course of a day. Why is there a capacity? For example, it could be that this is the 401, so it's a very fast road. So if I have enough trucks, I can send a lot of stuff this way. But this could be like a country road. So the road exists, but I can't send too much stuff. So for the sake of argument, we're thinking about how much data, how much goods can I move during the period of a day. Now, of course, in computer networks, this corresponds to the capacity of a link. So this could be a OC3 fiber optic link, very high speed. That could be a dial-up. Obviously, there's quite a bit of difference. Okay. Now, what we're concerned about is that we want to have these two distinguished nodes, which are always denoted by S and T. S is the source, and T is called the sink. And what we want to do is that the source has some amount of goods, in our case, an infinite amount of goods that it wants to send to the sink. And we want to find the assignment of the capacities to these paths such that we maximize the amount of data, amount of goods flowing from the source to the sink. Okay, just to give an example of this, so let's say I have some amount over here. Can I make this like this? So I have some set of arcs over here, and that determines how much I can pull out from this warehouse, the source warehouse. I can send them both over here, and let's say I send some over here, some over here. Now, one might argue, what I should do is to put, everything, saturate both of these links over here. Well, you could, but if these two links have little capacity, there's not much point. It's all just going to build up in these warehouses. Okay, even though we model it as being infinite, we really don't want them to overflow. So it's better not to send too much. We don't want to have overflowing warehouses. Okay, so we just want to find sort of the mathematically, essentially, what is the capacity? If I were to replace this whole thing with a virtual link from the beginning to the end like this, what is the capacity of this virtual link, given that the intermediate links have some capacities? Okay, so so that's the modeling of the problem. Okay, and so it sort of roughly models in computer networks, or roughly models a road network, but we're just interested in sort of at this stage a graph with some vertices and some edges, and each edge has a capacity over here, C, and we want to make sure, we want to assign some flow F to it, okay, and you have to make sure that the flow does not exceed the capacity. Obviously, you can't do that, right? The capacity is a constraint, and so we want to know what flows do we assign onto this whole graph so that you maximize the amount of flow between the source and the sink. Okay? So now already we're starting to get into the language of modeling. Okay, what are we modeling? Okay, well, let's think about it. Let's say we have some vertex I and some vertex j. Then we know that so we'll call the vertices I and j. We know that the capacity, this is a constraint, this is given to us. This is a fixed value. The capacity is Cij. Okay, so that's my modeling. So I've been told this road can carry so much, or this link has this bandwidth. I can just put that down as Cij. What can I change? How much? What can I do? I can assign different amounts of flows to different links, right? So again, it's obvious that my variables, my control variables, are the flows, and I'll call them Fij. That's the amount of flow sent from I to j. Okay, Fij is the amount of flow from I to j along that link. All right, and what do I want to maximize? I want to maximize the total amount of flow in the from source to the sink. Okay, how do I do that? Well, the source is called S, so I want to sort of know who are the neighbors of S. Okay, who are the neighbors of S? And if I maximize the amount of flow out of the source, that's the same as maximizing the flow across the whole network, right? I don't really need to worry about anything else, because I'll start putting in some other constraints to make sure that I'm not going to overflow anything else. So the objective will be to optimize the flow out of the source. But before I do that, let me kind of tell you the other constraints that we have. In fact, we only have one more constraint, which is that if you look at any node over here, let's say this particular node over here, it has some amount of flow coming in like this, and it's going out like that, right? Okay, so all I need to make sure is the total incoming flow does not exceed the total outgoing flow. In fact, I want to make sure that the incoming flow is the same as the outgoing flow, right? In an equilibrium system, whatever is coming in has got to go out. I don't want anything stuck in that warehouse forever, right? Otherwise, if it's less, then I'm wasting capacity. If it's much, if it's overflowing, the warehouse will build up. So obviously I have to make it equal. So what I'm going to do is I'm going to have another, basically I'm going to have this operator that exists Ij. Okay? That exists Ij means that there is a link from I to j. That's obviously. So the capacity, the constraint, the other constraint, okay, the one constraint I'm going to have is that Fij greater than or equal to 0 for all Ij. Well, obviously flows cannot be negative. I can't take stuff out, so the flows are positive. And then what I'm going to do is that the sum over all the flows coming into some node, let's say this node over here is I, and it has some previous node k, next node is j. So summed over all k such that there exists ki, right? The flow ki, this is the total amount of flow coming into node I, should be the same as sum for all j that exists Ij Fij. This is the conservation constraint. Means all flows coming into I must exit. Okay? So this is just, for example, in this node over here, if I put some numbers over here like this, let's say this is 1, this is 2, this is 3, 4, 5. An example of this is basically saying that F23 equals F34 plus F35. Okay? That's all there is. Okay? Because those are the links that exist. 2,3 exists, 3,4 exists, 3,5 exists. 2,3 should equal 3,4 to 3,5. Or another way of putting it is F23 minus F34 minus F35 equals 0, for example. Okay, and we can write those down. And now I have enough notation to define the optimization. I have to find all the guys. So objective function O is basically maximize, okay, sum that exists S, K, F, S, K. for all flows, for all k such that there is an edge from S to k, that's these two guys over here, 1, 2, and 1, 6, for example. I want to maximize fs2 plus fs6 over here, and that gives me the objective function. Okay. As you can see, the objective function is a linear function of the constraint of the control variables, fsk. Okay. And there you have it. I just sit down, I model it in a few, it doesn't take very long to model it. I just have to write down the objective function, the constraints, I throw it into a linear programming solver, and it spits out the values of the fij's. That's the solution. Now, it's not as elegant as max flow min cut, but it gets the job done. Okay. So before I comment on this, I want to go back and kind of get your response back on this. So, okay, so when you looked at the initial problem, we said, okay, maximize the amount of flow through the network. Okay. So how do we find the control variables? Okay, how do we get the f's? Right? Okay, anybody want to answer this? So in the problem, how did you find that this is the right modeling? Right? Is it too obvious, or? Okay, so I guess maybe I should answer that because I'm not posing the question properly. You want to know what knobs you have in your hand. What can you control? Okay, what you can control here is the flows. That's the only thing you have. So that's why you choose that over here. So when you get a problem, you have to ask yourself the question, what can I control? Okay, that's the most important step. What can I control? Once you have that, then you know what the modeling is. You can make these into the flows or whatever it is, right? The second thing you have to ask yourself is, what constraints do I have on my control? How far do the knobs turn? Are knobs linked to each other? Is there a combination of settings that are allowed or not allowed? Or how are they linked up? That's the second thing you need to know. And over here, these are the constraints. We have this, it's positive. And then this one, you have to think about a little bit, saying, okay, I have to conserve flows. And that gives us these equations. Once you do this, you quickly realize that this is linear. It's a linear equation. This is a linear equation. And thankfully, the constraint, the objective function is also linear. Once you see this, you're basically done. You just say, okay, I'm going to toss it into a solver, and I'm going to get an answer out of it. Okay. And this is the way we use linear programming. It's a big hammer. Okay. Whenever you find a system that you want to optimize, you try and say, okay, is there a way to cast it in the form of a linear program where I can just assign variables? And the nice thing with linear programming is we can deal with hundreds of thousands of variables. Okay, you can say, okay, I'm going to put a variable for anything you want. Okay, as long as it's controllable, it's fine. Just stick it in. And typical linear programs, you can, so constructing a linear program is quite fun. You can say, okay, that's a variable, throw it all in. And even if it's thousands and thousands, it's not a problem because you can still solve it. And as long as the objective function is linear, constraints are linear, we're in good shape. Okay, it just works out. And so I'm just explaining how to do that, over here, giving an example of network flow, which is a typical thing. It's an example you may not think of as being something you do linear programming, but in fact you can. Okay. Any questions about this? Yes. What's your name?
Direct graph. I mean, if you can push flow from, for example, from node 3 to 4, or you can push back from 4 to 3.
In this case, I am actually doing it for undirected. Okay. Or you can think of it as bidirected if you want. You can think of it as like this. So I have Cij and Cji. I don't really care. Right? So it's a directed graph, but I can assume I have it just in both directions. And then, because capacities may be different in different directions. Okay. So that's one way of modeling. It's a modeling question, how you want to model it. Yes? Oh yeah, that's right. I forgot. Yes, yeah. That goes with here for all ij, fij, yes, less than or equal to cij. Yes, that's why I had that in the first place. Yes, I forgot. Yeah, but that's again, it's linear. Okay. Any other questions? Okay, I'm going to now start on this topic of integer linear programming. and then I'll just kind of give you an idea what it is, and then we'll kind of continue with that next time. So linear program is some O and then AX, some A and some B. Okay, and sorry, O, X, A, B, some objective function O, control variables X, and the constraints expressed in the form A, B. Okay, and these are all matrices. Well, O is not a matrix. Anyway, integer linear programming is ILP is exactly the same except X, Xi belong to I. They're all integers. In the linear programming, in regular linear programming, Xi's can be reals. Okay, whereas in integer linear programming, Xi's are integers. So you say, okay, no big deal. Okay. So linear programming is order n cube, is the ellipse method. Integer linear programming can't be that hard, right? It turns out that integer linear programming is NP hard. Okay. In other words, linear programming is P, it's order n cube. But ILP is NP hard, okay? And this is, so, beginning students kind of are confused, like, oh, how could that be? Linear programming is, no big deal. You find the polytope, you kind of find your vertices, and you're done. Why is integer linear programming so difficult? What's the big deal? And the reason why integer linear programming is hard is because integer linear programming corresponds to systems where we actually have to try everything to find the solution. Okay, making the Xi's to be integers means that we can't just interpolate between any 2 points. We don't have this nice property that we can go and say, okay, anything along this line is fine. You have to be either here or you have to be over here. So if you have a space of solutions, maybe I should draw that over here. Like this again, going back to the space that we had earlier. Okay, I had that space, constraint space. I could go epsilon over here in this direction and see what happened, right? In integer linear programming, I don't have that. I can't just go epsilon in any gradient or any direction. I've got to go one full step, okay? And when you go one full step, everything can go completely different. It can be completely different solution altogether. An example of this that that may be intuitive, maybe a bit more intuitive to you is, let's say you have a meeting that has to be attended by 10 people. Okay, each of them has constraints of when they can attend and when they cannot attend. Okay, and you find a convenient meeting time. If one person changes and say, "Oh, I can't come that time, sorry," what happens? Right? Because they can't meet at the time, they have to find a different time, which affects somebody else, and so all of these non-interconnected pieces of the thing, so all parts of the system are connected to each other very tightly. So you change one thing, the whole thing falls apart. Okay. Another example of this is a Rubik's cube. So you have a cube that's almost solved. You have one cube out of place. You turn one thing, and then everything goes haywire. Okay. That's the structure of the problem. Or in another situation where scheduling is kind of the place where it really shows up a lot, not just scheduling of people, but scheduling of packets. If you choose a particular schedule of when to send things to maximize something, optimize something, you change one thing, everything else will change, because you have the structure that some element is linked to some other element, and those elements are linked to other elements. And if you change this guy slightly, all the others need to change as well. And so to find the optimal solution, the best solution, you need to change this and then propagate the changes out and keep doing this, okay? And it can end up in really, really complex situations. So a brute force approach ends up having to try all possible combinations of everything, and of course that is going to be NP hard, okay? So what I'm trying to give you is sort of the intuition of why ILP is hard, okay? And so when we have a problem, it's nice if it's a linear program. It's not nice if it's an integer linear program, okay? So if you have a problem, you say, okay, great, I can solve it because it's linear variables, it's great. But if you say the constraints are such that it must be integer solutions, right? In the case of the network flow, for example, the flows could be real numbers. It's no big deal. If it's a real number, you can just give it it's not a problem because we can deal with fractional flows. But with schedules, we can't have fractional schedules. I can say either you're here or you're not here, right? That's all you can do. So whenever we have these kinds of binary type decisions or integer constraints, okay, or logical constraints, true or false, then you can immediately see that it becomes an integer linear program. Just a simple example like satisfiability, okay, 3-sat or whatever, n-sat. 3-sat can be modeled as a ILP because you just take each variable, set it to 0 or 1, and you write out the equations one by one. And you can see right away that since you can express 3-sat as ILP, ILP is NP hard because 3-sat is NP hard, right? So we kind of get the reduction right away. So when you get ILP, then you're kind of in big trouble, okay? So what I'm going to do next time is to give you first intuition. This is the intuitive explanation of ILP, why it's hard. And the next time I'm going to give you an example of ILP with scheduling, and then I'll talk about some tricks you can use when you have an integer linear program that will allow you to get around it. Okay, so that's basically all for today. Are there any questions about this?